But now I want to talk about ray tracing for another kind of object that can also produce images. Not only lenses can produce images. Turns out a mirror can also produce an image. So you know that a flat mirror definitely produces an image of an object. If you have this object in front of the mirror, then you know that the light coming out of that object is going to hit the mirror at a certain angle. It's going to bounce back with the same angle. If this is theta, then this is going to be theta again. And that if you project that and you look at another light ray and how it reflects, for an observer over here, those light rays, the ones that are bouncing back from the mirror, seem to be coming from this point. So that's where, sorry, should be, do it a little bigger here. So that is an image that is virtual. And for a flat mirror, it's also upright. And the size of the image and the size of the object are the same. And the distance between the image and the mirror and the image between the object and the mirror are the same. Now, when you have a curved mirror, things are not like that. So I have a curved mirror here. So this is the first kind that we're going to talk about, which is called a concave. Kind of looks like a cave, right, where you could seek shelter. So that helps me remember. I don't know if that will work for you. Certainly worked for me. That was really great to think about that, because I always kept mixing them. So since it's shiny, the surface is shiny, then the light ray coming in should be reflected. And if you look at a very small region of the mirror, it kind of looks flat. If you're an ant sitting at some point, it kind of looks flat, the same, for the same reason that the Earth looks flat to us ants on the surface of the Earth, even though it's curved. So a light ray that hits a particular spot on the mirror should be reflected with an angle that makes from the normal to the surface with an angle that is the same. The incident angle is the same as the reflected angle, right? Gotta wait a little bit for that. So that is clear, I think. But now the problem is that you have the surfaces, the direction of the surface is changing. So two light rays, if one hits here, it's going to find a mirror pointing in one direction. That section of the mirror is pointing in one direction. But a different light ray that hits at a different spot is going to find the mirror pointing in a different direction. Think about the one that hits the center. The one that hits the center finds a surface that is perfectly vertical, and it bounces back that way, right? But a light ray that hits on this side, for example, you can tell that the surface of the mirror at that side is like this. So a light ray that hits here, it's going to be reflected that way, right? So you can see that one light ray bouncing this way and another light ray bouncing this way. They're going to meet each other at some point in front of the mirror, right? So as I said, the angle of incidence is equal to the angle of reflection. And if you have two light rays hitting the mirror parallel, they're going to intersect at some point, right? The point where they cross each other is the focal point. If I had more of these lasers, then you would see I could illuminate from all different directions, and you'll see that all the light rays are going to hit or intersect at one point. Okay. So how is that? Well, for the same reason that a lens can produce an image of an object. So let's draw that mirror over here. As before, the symmetry line, we call it the optical axis. Let's put an object somewhere here. The focal point of this mirror, let's say that is there. And you could check in your book for a derivation of this simple formula that tells you that the focal point, the focal length is equal to the radius of curvature of the mirror divided by 2. So the center of this circumference here will be somewhere here, right? Half of that distance is the focal point for that mirror. That's the point where parallel light rays get focused. Okay? So if you have an object over here, as before, that object is shooting light in all directions. And some of those light rays since the center of a mirror is vertical, whatever angle you have here is the same as the angle down here, so that's easy to draw, right? You could just look at this angle and draw another line underneath the optical axis that makes the same angle. And that will be a way to verify that you found the image at the correct location. This is the object, this is the image. So what does this behavior look like in terms of comparison between a mirror and a lens? The parallel light rays that hit this kind of mirror, which is called concave, get focused at one point. So that's the behavior that converging lenses have. Parallel light rays get focused at one point. And because of that, the behavior of this mirror is very similar or almost identical to the behavior of a lens. If the object is placed at a distance from the mirror that is greater than the focal length, then the image of the object is going to be inverted. Just like in the case of a converging lens. So this is similar to converging lens. Following that analogy, maybe you can guess what's going to happen if the object is placed very close to the mirror, to a concave mirror. Do you notice anything? And is it upright or inverted? Your image is inverted? Okay. How about now? Okay. How about now?
Oh, it's upright.
It's upright now, right? And at some point you can't see anything. And if you're further away, then you can see an image again, but it's inverted. So it's changing from, it's happening the same thing with a converging lens, right? When you have an object and you look at it with a converging lens, if the converging lens is really close to it, then the object is upright, right? When her face was really close to the concave mirror, she could see her face and it was upright. And it was magnified, actually. But once you take your lens, the converging lens, away from the object, then the image of the object that you see with the converging lens will be inverted. The same with this mirror. When I look at it at this distance, I see my face, but it is inverted. Okay? And when I get closer, it's again upright. And in between them, what do you think happens? Why can't you see anything at the intermediate point? Exactly. The image is coming, it's formed at infinity, the light rays are coming in parallel after they bounce off the mirror. So it's neither upright or inverted, it's just no image. That will be the case here. For example, this is the focal point. Optical axis. The object is here. So you do your parallel ray hits the mirror, bounces towards the focal point. This one doesn't really hit the mirror, but if the mirror was bigger, it would. So that's okay to draw it. Hits the mirror, turns parallel. So remember, it is okay if the size of the lens does not allow you, because you draw a light ray, this one should be coming or seem to cross the focal point, right? That light ray doesn't hit this mirror. So in a problem, in an exam or something, if you try to do one of the principal light rays, you might not be able to draw because it doesn't hit the mirror. Ignore that and go ahead and draw it. Because remember that the image is not formed by the principal light rays alone. There is an infinite number of light rays in between those two that are also bouncing off the mirror, and they're converging or seem to be converging at the same point. So not being able to draw one principal light ray is not a problem. So just go ahead and draw that one. You can do another one, which is this one. Okay, and I didn't do it very strongly because I don't know if that's going to be exactly right, but continue this. Continue this one. And they seem to intersect somewhere back here. And as I said, you could check that work by drawing this one. And if you continue, that one should be also intersecting at the same point. So for that object that is closer to the mirror than the focal point, then the image is going to be here. And it's a magnified image, and it is upright. So that kind of mirror can work as a magnifying mirror. Unfortunately, I don't have a convex mirror to show you. But the idea with a convex mirror is that, well, you're going to use the other side of the mirror, that is the side that curves out. That is the part of the mirror that it's going to be reflecting the light rays. And if you have parallel light rays hitting a convex mirror, then those parallel light rays, after they hit the mirror, they diverge. I mean, they get reflected. But they get reflected in a particular way, which is that they all seem to be coming from the same point. So that's what a convex mirror will do to light rays that are coming in parallel, right? There is a point, again, the focal point, which is equal to the focal length, sorry, it's equal to r divided by 2. And you're going to use a minus sign for that when we use the thin lens equation. So not to forget that. And this kind of lens, of course, can also make an image of an object. if you place your object, say here, then you can follow the light rays. You take the parallel one. Gets reflected that way. You could take one that hits the center of the mirror, and that gets reflected at the same angle underneath the optical axis. And you could take the light ray that heads towards the focal point, because that one gets reflected parallel to the optical axis. When you project these light rays back, they seem to intersect at one point, not surprisingly. And that point is where the image of that object is going to be. So in this case, it's going to be a smaller arrow, and it's on the other side of the mirror. Just as in the case of the concave mirror being similar to a converging lens, the convex mirror is similar to a diverging lens. So every time you have a real object, physical object that you put in front of this kind of mirror, you will get an image that is upright, and always smaller. So today when you're having lunch, you can grab a spoon, and that's a good mirror, and it has both of them, right? It has the concave part and it has the convex part. So you can try that and see, for example, you could be able to tell what's the focal length of the concave part by doing the little experiment that we just did. If it's far away, the image of you or your face of the people behind you should be inverted, right? And right at the point where you can't see an image, that will be the focal point, the focal length of the spoon. And then you turn it on the concave side, and you will see that no matter what distance you hold the spoon, your face, the image of your face would be upright, and things seem to be crammed into a small space of the spoon. Everything seems to be smaller in size. Okay?